depending on how you count, we're either halfway there for the total of 12 videos we'll be doing this week, or we're 60% of the way there if you're only thinking about countability. This is a little bit of an aside, this video. You don't need to know this to understand the following videos, though I think it's really, really useful information. And it's something you will probably need to know to do the homework really effectively. I think it's also a really useful set of exercises for really understanding the properties that we're looking at. Okay, so what we're going to do today is talk about inverting functions. So we've already seen an operation on relations, right? So if R is a relation from A to B, then R inverse is a relation from B to A, defined as R inverse is the set BA if AB is in R. So that's with set builder notation. We might also say that, let's do it this way, B R inverse A if and only if A R B. So it's just really swapping the positions. We've already seen that functions can be seen as sets of relations, so it makes sense to think about the inverse of a function. So we'll do that here for just thinking about unary functions and thinking about their inverses, though you can, of course, give a story at a higher level. Right, so we could write down, if we wanted to already, just like what these inverses would be, just to get a sense. So like, let's see. So square inverse is going to be those y x such that, okay, that the square of x, oh, nope, that's not what I wanted, is equal to y. Okay, so you can think about that function for a minute. You may have an intuition already for what square inverse looks like. I'm just going to write down all the inverses first, and then we'll take a minute to look at how their properties work out. Okay, suc inverse is the set of what? N plus 1 to n, where n is a natural number. Pred inverse, okay, what is that? Well, it's the flip of whatever pred n does. So to me, it looks something like this. But I'm trying to give you a variety of different notations. Okay, so swap, what's that going to do? Swap inverse, what's going to do the opposite of what everything does. So we can see swap inverse of, here, let's just do this, is equal to mn swap n equals m. Right, and if we wanted to think about that for a minute, another way to write this would be swap inverse of m equals, well, okay, what's swap going to do? We have to do the same cases. If m plus 1 is even, so if n was even, then we'll return m plus 1. So if m is odd, we'll do m minus 1, and if otherwise, we'll do m plus 1. Now you may notice something interesting about how swap inverse and swap relate, and we'll talk about that in a minute. Okay, so we've just seen that these things exist. There are a bunch of questions that we might ask about these. Are these functions? Right, they're absolutely relations. There's no question about that. But we need a bunch of properties for them to be functions. In particular, we need determinism, right? It shouldn't be the case that there's more than one thing here that something here maps to more than one thing on the other side, right? That we need that determinism property. And then we might also ask, if they are functions, what properties do they have? Right, so in particular, we're thinking of things like totality, injectivity, surjectivity. Now, it's a good exercise, if you like, for you to pause the video right now and think about this for yourself. Just think about it concretely for each of these. Look at these. Which of these are total functions? Which of them aren't? Which of them are injective? Which of them aren't? And which of them are surjective? And which of them aren't? And if we'd like, we can take a minute to sort of recall the things that we know about the functions over here. What are the properties we know about these functions, right? Which of these are total or not? So all of these functions we decided were total at first, though there were variants of pred prime that you could think about now if you wanted to. So I'll just make a little t for total. And then now which of these were injective and surjective? So square was neither. Successor was injective but not surjective because it missed 0. Predecessor was surjective but not injective because there was more than one thing that hit 0. And this swap was both. Okay, and now if you like, make a similar chart for those functions on the right and see if you notice any patterns. Okay, pause the video, do that, think about it. It's a great exercise. You'll learn a lot. Now I'm going to show you how to get the answers. Okay, so the general idea is that what we can do is just work through the consequences of each of these properties. So what I'm going to do for each of these, I'm going to write down the property, and I'm going to see what it means, right? And it'll tell us some property about f will tell us some property about f inverse. So I'm going to do that for each of the 3 properties we care about here. Well, really what we want to look at is total and deterministic and injective and surjective. We'll see that there's just a direct relationship between these bits. Okay, are you ready? So let's start by thinking about totality. Right, so what does it mean for f of type A arrow B to be total? F of type A arrow B is total if and only if for all A in A, there exists a B in B such that A, B is in F. Here, let me actually write that in a nicer notation. F of A equals B. Okay, but that really means, what do we mean by that? It means what I wrote the first time for all A. Let me move this up so I can get a better writing position. For all A in A, there exists a B in B, A, B in F. Okay, what does this tell us about F inverse? Well, it tells us this about F inverse. For all A in A, there exists a B in B. Oops, I used colons earlier. I'm just going to correct that real quick. There exists a B in B such that BA is in F inverse. That's just how we defined inverse up here, right? That's the definition of inverse we see over here. Okay. So if you recall, this is the same thing. Oops. As saying that F inverse is surjective. Because recall that F inverse is a function from B to A. And we're saying that for everything in A, there exists something in B that maps to it. Wait. So what I want to note is that the totality of an original function of f is surjectivity of f inverse. Interesting. There's sort of this mirror between these two properties, right? That totality for the original function is surjectivity of the inverse function. Interesting. Okay, let's look at determinism or functionality. Right? This is the thing that makes something a function. Okay, what do we know? Okay, f from a to b is deterministic. Okay, what does that mean? Well, that means for all a in a, for all b1, b2 in b, if a, b1 is in f, and a, b2 is in f, then it must be the case that b1 is the same thing as b2. Okay, this is the thing that justifies the function notation that we've used. All right, let's carry this out and start to think about what it would mean for the inverse. Okay, well that means that, okay, for these same for alls, for all a in a, for all b1, b2 in b, b1a in f inverse, oops, and b2a in f inverse implies that b1 equals b2. Right, we can write this maybe a little more familiarly. I'll swap the orders of the quantifiers here. I'll use function notation and just drop actually the quantifier for a because I'll just say what it's equal to. And then we'll find that b1 equals b2. All right, so this is going to be the case if and only if f inverse is injective, where here we again have f inverse of type b arrow a. But so we got here to injectivity of f inverse. Oops, that's a little messy. Okay, cool. So what I want to note is that we have a thing here that mathematicians call duality. Where basically duality is kind of the property you get of a mirror image of something, right? That totality is dual to surjectivity, and determinism is dual to injectivity. Okay, so I wrote here we have something like, oh, this is of f and this is of f inverse, but if you sort of like swap these, injectivity of f gives you determinism of f inverse, and surjectivity of f gives you totality of f inverse. So what does this tell us? Let's like use this to sort of summarize the things that we should then be able to simply know about a function. So f a arrow b injective, what does that mean? Well, if it's total, if it's injective and total, that means that what we should get out is that f inverse is surjective because totality dualizes to surjectivity, and because it's deterministic, we'll get injectivity. Injective, and we'll get deterministic because f itself is injective, and dually that'll be deterministic. But may be partial. Right? If f is an injective function, a total injective function, then its inverse will be surjective. Something's... Yes, will be surjective, injective, deterministic, but may be partial. Similarly, if f from a to b is surjective and total, okay, then f inverse, well, because it's surjective, is total, right? Everything in the codomain B is going to be accounted for in the domain of the inverse function, right? That's the dual of surjectivity. The inverse, because f was total itself, the dual will be surjective. Because f is a function, it will also be injective. But maybe not functional. Okay, so then we can finally sort of conclude by conjunction that if f a b bijective and total, then f inverse is bijective and total. Right? So bijective functions have well-defined inverses. I want to make one tiny note here before I return to the examples, and we can sort of explore what it is that what the consequences are here for that. Which is that this exists. This sort of idea that these functions exists is a sort of a mathematical implication, not a Coq implication. Just because f inverse exists doesn't mean you know how to write it down or compute it. Okay, so let's scroll back up and sort of look at the consequences here. So we saw that square, this SQ function, was merely total. So that tells us that the dualization of that, right, the inverse of that, it's because it's neither injective nor surjective. What are we going to get out of it? Well, we don't really get anything. So what properties do we have of the resulting thing? It's not even going to be a function, right? Why not? What properties do we have here? So like, is it a function? So let's just record for each one of these whether the inverse is I'll write it over here. Sorry about the confusion, folks. Okay, which of these are functions? Which of these are injective? Which of these are surjective? Okay, this is neither injective nor surjective. The square inverse function, how many y's are there such that that square of x equals y? Well, it's going to be all the positive functions, so it's going to be partial. Or here, let's phrase this positively. Right? Is it sort of total in the domain? No, it's not going to be total. Is it going to even be a function? Well, no. So how many numbers square into 9? 2, 3, and -3. So square inverse of 9 is going to not even be able to return you one answer. There's two different numbers. So it's not going to be functional, and it's definitely not going to be injective or surjective. Okay, successor. This is a total function originally. Its inverse is not total. It's a partial function, but it is a function. Okay, it was injective. Is it still going to be injective? So in this case, the answer is yes. Will suck inverse be injective? Are there two numbers that get you to the same answer? No, right? There's a unique predecessor, but it is a partial function. Will the result be surjective? Again, the answer is yes. Every number has a number that's one greater than it. So we get a partial function out that happens to be injective and surjective. What about predecessor? Okay, it was a total function. Is the thing that we get back out a total function? Well, it is total, but it's not a function. Right? In particular, 0 maps to itself, and it also maps to 1. Right? So that also is going to, what does that mean in terms of surjectivity? Well, it is a surjective function that we get out. Is it injective? Well, let's think about that. 0 maps to 0, and 0 also maps to 1. That's fine. That actually doesn't mess with injectivity. Otherwise, and it's not a function, but it's still a relation could still have that injective property. Otherwise, every number will map to something unique, so it will be, in fact, injective. Okay, swap inverse. This is the last one. Okay. Swap was total. Will swap inverse be total? It's like, well, if you take a second and look, swap inverse is the same function as swap. So yes, it will be total, and it will be a function, and it will be injective and surjective. Right, so this is the golden row. The other rows, I think, are very hard to understand. You heard me hesitating as I worked it out in my mind. It's pretty complicated. The main takeaway that I'd like everyone to have if I can ever spell the word takeaway. Bijective functions are invertible. Secondary takeaway. Duality tells you a lot. Okay, that's it for this video. I'm sorry it was a little bit touch and go at the end, a little bit confusing. This is all we really need to know about invertibility. Next up, I'll be talking a little bit about cardinality and how we'll use functions to establish relative sizes between sets. So we'll have those two videos, and then after that, we'll talk properly about countability and how you prove it, and then uncountability and how you prove that. So we are in the home stretch, about to start learning the thing that is the main thing for this week. Thank you for bearing with me. Cheers, y'all.